Hey guys, what's up? Sorry about the technical difficulties. Hopefully everybody can find their way over here. Posted a link in all the places. Hopefully it's all good now. So wait for everybody to show up. Hopefully it's gonna work this time. Looks like everybody's finding their way back over to the new one. All right. Just send out a notification, make sure everybody gets the new stream. So, all right, so the exams are under construction. That's the wrong word. They are processing, we'll call it that. So about halfway through, a little more than halfway through. I grade everybody's problems 10 to 5 last night, and then I'll try to get the rest done today, hopefully. But so far, it's decent. I had a few really good scores and a few missing a lot of problems. So hopefully we can make up some ground today. Also, we got a little behind because I did a review, so just trying to make up some ground as well. Hey guys, so let's see. Chapter 4, we're going to try to get through chapter 4 pretty quickly if possible. It's going to be all the continuous distributions and continuous ideas. We talked about in chapter 3, that was all the discrete stuff. Well, now we're going to do all the continuous stuff. And then chapter 5, we finally start doing statistics. So this is all the probability background, or the side of statistics that's really important for the theory to work. So we're gonna finish up with this one last chapter before we get into statistics. So this last chapter is all about probability, and in particular continuous probability distributions. So basically think about this. If you want to think about an infinite number of possibilities in this interval, infinitely many outcomes. So infinitely many outcomes. And it's actually uncountably many. Uncountably, infinitely many outcomes. Then the probability that you take on any particular value, it's going to be 0. You could think of it like this. If you're on the interstate, and let's say this is Los Angeles, and this is, let's see, where does that go? That goes somewhere in South Carolina. So we'll go to Atlanta, ATL. This is the Interstate 20. So this is I-20. What's the probability that you have an accident right here in Jackson, Mississippi? That's kind of the idea. Like, you could take on any particular location. What's the probability you have an accident right there in Jackson if you're driving all the way from Atlanta to Los Angeles? Well, I don't know. It depends on how do the accidents distribute. So probably a lot over here, and then kind of goes up here in Dallas, and then probably around Jackson, and goes up again in Atlanta. So what's the probability you have an accident right here in Jackson? Well, if I took a very small amount, I would be able to figure out what's the probability that you have an accident right there in Jackson. Furthermore, what's the probability you have an accident right there in Jackson on top of a certain bridge? Like, it's even smaller. So you cut down, you get even smaller. Well, you have infinitely many outcomes. You have one particular outcome you want to look at. You have infinitely many outcomes. You take 1 over infinity. It's basically 0. So this is basically 1 over infinity. So that's why the probability is equal to 0, more or less, for an infinite number of outcomes, or a continuous random variable. So examples of variables that are continuous would be something like distance traveled, depth of a lake, pH of a chemical, waiting time at a bank. These are easier to work with, so we use integrals instead of summations. Well, what's the difference? Well, an integral is a limit of a summation. So it's a little bit easier because we can do everything symbolically and not have to write all the sums out by hand. So it's more like, you could say, the limit of a histogram. As you make smaller and smaller divisions, you get, you know, closer and closer to the continuous distribution. So if you do something like that and you keep cutting it, you know, you might get closer and closer to the actual distribution or whatever's going on, you know. So that's if you were to make like smaller and smaller cuts on the x-axis. So now it's like infinitely many bins. This is finitely many bins. So smaller bins and even smaller. So that's kind of the idea, is it's like a limit of discrete. That's one way to think about it. You just took your discrete distribution and you just cut it up and you say, okay, what if I look at these smaller intervals, smaller little bins, smaller sections, till I get down to so small, like differential dx, and then it's basically a continuous thing at that point. So definition, what is a probability density function or probability distribution function? So the definition right here is let x be a continuous random variable. A probability distribution or probability density function, PDF, of x is a function f of x such that for any two numbers, a and b, a less than or equal to b, we have that the probability x between a and b is the integral from a to b f of x dx. So this is the key idea. You calculate probabilities by integrating a density function. So similar to calculating mass, you just integrate the density. Well, now we call it a probability density because the probability is distributed over this direction, this x direction. So as the probability is distributed, to get the probability, you would have to multiply by some length. So this is a length. So length. And then to get the probability, you multiply the function, which is probability per length, times length. So probability per length as a function of x, and then to get the probability of x being between a and b. So the area under the curve is the probability because the probability is distributed per length. So as you change your length, you get different amounts of probability because it's a probability density. It's distributed over the x direction. Now, conditions are, number one, down here, the density function f has to be non-negative for all x. The second condition here is that the integral of the density function over the whole real line should be equal to 1. So the integral of the density function over the whole real line has to be equal to 1. If those two conditions are satisfied, then we can call it a probability density function. So let's look at an example. This is called the uniform distribution. The uniform distribution. So the example says the random variable x follows the uniform distribution on the interval AB if the PDF of x is f of x AB, which is going to be equal to 1 over b minus a for x between a and b, and 0 otherwise. So think about this. This length down here is b minus a. So that's the length. This is the density function value, f of x. It's constant. So the area of this rectangle is going to be 1 over b minus a times b minus a, which is 1. So the total area of this box is equal to 1, which is basically the integral that is done down here in part B. So doing the analytic integral, you get the same answer. But I shouldn't say A, I should say the area of this box is 1. Well, that's the same as if you're to do the analytic integral. The function is non-negative because it's 0 if you're outside of a and b, and it's 1 over b minus a if you're between a and b. So the function is always greater than or equal to 0, so that's good to go. Part B, if we actually do the integral down here, then integral from negative infinity to infinity, f of x dx, would be integral from minus infinity to a, 0 dx, because between negative infinity and a, our function is 0. Between a and b, the function is just 1 over b minus a over here. And then from b to infinity, we're 0 again. Now, all we got to focus on is this middle integral. And what is the function right there? The function is 1 over b minus a for x between a and b. So this integral, this is really just a constant. 1 over b minus a is just a constant. And what can we do with constants? We can pull them out of the integral. So I pull the 1 over b minus a out, and now I'm integrating 1 dx. And integral of 1 is x, and that's x evaluated from a to b, which is b minus a, which is 1. Check. So this is indeed a PDF. So this tells us f equals 1 over b minus a is a PDF. So that's how we check to see whether or not a function actually is a PDF. Right, so example. I'm not going to worry about the part C. So this is not really necessary. We can just kind of skip this. But it's just like a proof to show that the integral from c to c would be 0. So basically, integral from c to c would be 0. And we already know that from just doing integral properties. Basically, delta x would be c minus c over n, which would be 0, which means our integral from c to c would be 0, because we take the limit of delta x times f of x. But this is just another approach to show that the integral would be 0. So what would this be? This would be probability x equals c. All right, so let's look at another example here. This example says the elapsed time, which is x, between the time a car finished passing a fixed point and the instant the next car begins to pass that point, called the time headway in traffic, flow management on freeways, is given by this function f of x. This function f of x is 0.15 e to the negative 0.15 times x minus 0.5, where x is greater or equal to 0.5. Now, show that this thing is a PDF, basically. Show that f of x is a PDF. Well, what do we have to do? We have to show that first it's greater than or equal to 0 everywhere. Let's see. E to the negative x basically goes like this. Let's draw it more like this. That's e to the negative x. So it's always greater or equal to 0. So if I shift it left or right, it's still greater or equal to 0. And if I multiply it by a positive constant, it's still greater or equal to 0. So this is good to go. Now the integral, that's going to be a little tricky. So let's look at the integral from minus infinity to infinity, f of x dx. It's going to be the integral from minus infinity to 0.5, 0 dx, plus integral from 0.5 to infinity, 0.15 e to the negative 0.15 x minus 0.5 dx. And I break it up this way because my bounds for my function up here say that if I'm less than 0.5, my function value is 0. And then this whole integral right here is going to be 0. Now I have to do the second integral from 0.5 to infinity, 0.15 e to the negative 0.15 x minus 0.5 dx. I think I'm going to do a u sub, say u sub u equals negative 1.15 x minus 0.5 du equals negative 0.15 dx. And we'll come back to the original bounds in a minute. So this will be the integral 0.15 e to the u negative du over 0.15. And this is going to cancel. And so this is going to be negative e to the u, which is negative e to the negative 0.15 x minus 0.5 from 0.5 to infinity. And really this is bad notation to write the bound as infinity up there. So we should be careful, and actually we should probably take the limit as t goes to infinity and let the upper bound be t. But we'll just break the rules for a minute. All right, so this is going to equal negative e to the negative 0.15 infinity minus 0.5 minus negative e to the negative 0.15 times 0, which is equal to, let's see, e to the negative infinity plus e to the 0. Well, that's 0 plus 1. So this function integrates to 1 over the whole real line and is non-negative. Therefore, f of x is a PDF. Good to go. Now, part C of this example wants to know what's the probability that x is less than or equal to 5. So we only have to integrate from 0.5 to 5 because if we go before x equals 0.5, f of x is going to be 0. So integral from minus infinity to 0.5, 0 dx plus integral from 0.5 to 5, f of x dx. So that's why we can skip the first part of the integral, negative infinity to 0.5. Just start integrating at 0.5 and go up to 5. So let's finish the integral here. It's going to be integral from 0.5 to 5, 0.15 e to the negative 0.15 x minus 0.5 dx. Same thing, do a u sub, u equals negative 0.15 x minus 0.5 du is negative 0.15 dx. And we're going to get the same integral as before. This is going to be negative e to the u, and so that's going to be negative e to the negative 0.15 x minus 0.5 from 0.5 to 5. This is going to be negative e to the negative 0.15 times 5 minus 0.5 plus 1, basically. So we already figured out when we plug in 0.5, we get a 1. And this is going to equal 1 minus e to the negative. That's going to be 0.15, negative 0.15 times 4.5. And we do a little plug and chug. So it'll be negative 0.15 times 4.5. So it'll be negative 0.675. And 1 minus e to that is going to be 0.490844 if we round it right there. So we'll take a second, try to soak that in a little bit, the u sub and everything. Hopefully remember how to integrate. We're not going to do any kind of like super crazy integration. U sub and integration by parts is pretty much all we're going to handle. And even not that much. Whenever we do, we'll just do a quick u sub or integration by parts. But yeah, just hopefully go over and remember how to integrate, try to do a little review maybe. But yeah, if you need help, just contact me. We'll set up like a meeting or something. We can kind of go over some integrals. But yeah, gonna need to know how to do some integrals for sure. So just take a second, soak it in. We'll see another idea in a second. Cool. I wonder if there are any questions. I got the chat open on the right. Looks like everybody's joined us now. That was on the other stream. 42 watching. I wonder if that's a sign. 42 watching. It's definitely a sign. Yeah. Okay, so the u sub. Let me just go over to like a regular integral over here. So like a integral e to the 2x dx. So to do this integral, I would do like u equals 2x. Because what do I know? I know that integral of e to the u du is just e to the u. So if I can turn it into e to the u, then I'll be good as far as my integration goes. So and then du dx would be just 2 if I differentiate u with respect to x. How do you know? We'll get there in a second, Taylor. So then I multiply, this is bad terminology, but I multiply and I say du equals 2 dx. So that's why I write du equals 2 dx right here. And then I say, okay, well, dx is equal to du over 2. So now if I substitute everything in here, I get integral of e to the u, and dx is du over 2, which is 1/2 integral e to the u du, but I know that is now 1/2 e to the u. But now I can substitute what u is, and that's 2x, so this is going to be 1/2 e to the 2x. So get some practice with u substitution. Going to be super important. Also, integration by parts. And then just review all your basic antiderivatives. For example, integral of cosine dx is sine x. Integral of x squared dx is 1/3 x cubed. Technically plus c, but we're going to always plug in bounds so we don't have to worry about the plus c stuff. So hopefully that helps a little bit. So just review u substitution, integration by parts, and basic antiderivatives, especially polynomial stuff. We're going to use a lot of polynomial stuff when we get to joint PDFs. Maybe some fraction stuff like integral 1 over x dx is natural log absolute value x. So that's another one we need. But just go back and review these concepts. They're going to be needed just to solve problems. How do you know when it's not a PDF? Well, if it's... Good question. Let me pull that over here. So f of x would not be a PDF if f of x were less than 0 for any value of x, or if integral from minus infinity to infinity f of x dx is not equal to 1. So either one of those, if you don't satisfy, then it's not a PDF. So you have to satisfy both of those conditions to be a PDF. It has to be non-negative, and the integral has to be 1 over the whole real line. Then it's a PDF. If you break either one of those, then it's not a PDF. All right, so that's a PDF. It's a density function. It tells you how the probability is distributed over the real line. Not just over single x values, but over all the real line. Infinitely many x values now. So 4.2 is cumulative distribution functions. So it's just the continuous side of cumulative distribution functions. The continuous side meaning the idea is the same in that it's accumulating probability like it was in chapter 3, except now we just do an integral instead of a sum. Yes, you're welcome. No problem. So integral instead of a sum. So integral instead of a summation. But the idea is the same. Probability starts to accumulate. So here's your PDF on the left, PDF, CDF on the right. The probability is accumulating on the right until we get to 1. And once we reach 1, we stay there. So stays at 1 forever after, because there's no more probability to accumulate once we go past 10. Probability stops accumulating. So that is the probability distribution and the cumulative distribution function. Cumulative distribution function. It's the integral from minus infinity to x, f of y dy. So basically the upper bound of integration is the variable. It says, okay, I want to accumulate probability up until a certain x value. Up to that x value, how much probability is to the left? of that x value. So how much probability is to the left of this x value? That's what this CDF tells me. So f of x is the answer. The integral from minus infinity to x. It's how much probability is to the left of x. And we can see that in the shaded region right here. That's the probability to the left of 8. So then what's the probability at 8 to the left? Well, it's this value right here, f of 8, capital F of 8. So that's the cumulative distribution function. So let's find the cumulative distribution function for the uniform distribution. So let's look at where x could be. X is the upper bound of integration. Let's see what are the possibilities for it. Well, x could be less than a, and that's the first one right here. If x is less than a, then f of x is equal to 0, because you have not started accumulating probability yet. No probability accumulating yet, because our function, our PDF, doesn't start until we get past capital A. So we haven't started accumulating any probability. All right, so now let's look at part B. If x is between A and B, capital A and capital B, then we actually do have to do something. We integrate from minus infinity to x, so minus infinity to x, f of y dy. Well, before I get to capital A, my function is 0, so I only have to integrate from capital A to x, because integral from minus infinity to capital A would be 0, because the function is 0 there. So then I only integrate from capital A to x. My function now is 1 over b minus a. So integrate that, pull the constant out again, and then I get 1 over b minus a times x minus a. So then it's x minus a over b minus a. So that's the CDF value for x between capital A and capital B. Now for x greater than capital B, we integrate from minus infinity to x, f of y dy, which is integral from a to b, 1 over b minus a dy, because that's the function value between a and b, and then 0 from b to x, because x is greater than b. So then this is what f of x equals 0 for x greater than b. So that's going to be 1 plus 0, which is 1. The first integral is 1 because it's a PDF. The second integral is 0 because you're integrating 0. So this adds up to 1. So that means for any x value greater than capital B, capital F of x is equal to 1. So then it's a piecewise function. Very similar to the exam problem, number 6, except we have a continuous function in the middle. So it's continuous function, whereas the one you graphed on the exam was a discrete function, but we still kind of plotted it like a continuous function. A lot of you drew a straight line. Some of you just drew a vertical bar. That's fine too. A lot of you drew like a horizontal line, I think like we did in class in the example. But this is truly a continuous function between a and b. Well, actually over the whole real line, it's a continuous function. So let's look at what its graph would be. So on the left, here's the PDF. Here's the shaded region, f of x, in the middle. And then on the right, here's the CDF. So now the CDF doesn't make discrete jumps. It makes a continuous transition. So it's a nice continuous transition from A to B. So it's a continuous transition. Unlike our discrete CDF. So unlike the discrete CDF, that you saw on the exam, and then we saw back in chapter 3 when we were talking about CDFs for discrete random variables. It's a continuous transition up from A all the way up to 1 at B. So it's a nice continuous transition. And then it stays at 1 because you're never going to add any more probability. So you never add more probability. So this is the cumulative distribution function. Now this idea of a cumulative distribution function is going to be so important, because all of the normal distribution stuff that we do later and so much of statistics is going to rely on the fact that we are using a cumulative distribution function. Like the table itself is a cumulative distribution function. So when we get to do all those tables and stuff like that, a lot of it's going to be from a cumulative distribution standpoint. So what we're going to have to do is start to use these cumulative distribution functions to calculate probabilities. So using a cumulative distribution function to calculate probabilities right here. So let's say x is a continuous random variable with PDF f of x and CDF capital F of x. Then for any number, little a, probability that x is greater than little a is 1 minus f of a. So this is like the complement rule, basically. Complement rule for continuous distribution. So what does the CDF tell us? The CDF tells us, say this is little a, this is capital F of a. Well, to get probability x is greater than a, I'll put that in green over here. This is probability that x is greater than a. Well, I know the whole probability under the curve is 1, so I do 1 minus f of a to get probability x is greater than a. Then the second one down here, probability that x is between a and b is actually f of b minus f of a. And I love this picture right here. This is a great picture. This is what we want. Let's see, f of b is right here, f of a is right here. So if I subtract away f of a, which is this shaded region here, minus, you subtract that from f of b, which is this whole shaded region, that'll give you what you want right here in green, which is everything between a and b. Now there's no weird, like step up or step down a discrete value, because it's a continuous thing. You can just subtract f of a from f of b. You don't have to like worry about the thing we did in chapter 3 with discrete CDFs. You can just subtract directly the number that you have right there. Even if these are not equal signs, even if they're strictly less than, it doesn't matter. It's the same thing. So this is the crucial idea, and the whole reason we want to introduce CDFs is to use them just like this. This idea of basically graphically looking at a CDF and subtracting a smaller value away from a larger value to get the value between two, like a and b. That's so important, so important. Understanding what the CDF does and how it's represented graphically and how you can use it to calculate probabilities. Extremely important. So let's look at an example. This example says, let's say we have a random variable x, and that is the dynamic load on a bridge in newtons, and it's given by this PDF, little f of x. It says that it's a PDF, but is it actually a PDF? Well, we can verify that this is a PDF. So let's see, 1 over 8. So we'll first verify f of x is a PDF. This is 1 over 8 plus 3 over 8 times x for x between 0 and 2. Well, this is just a straight line, shifted up 1 over 8, with a slope of 3 over 8. And then 0 everywhere else. So that's our PDF in red. So until we get to 2. So that's our PDF. So definitely it's non-negative. Number 1, f of x is greater or equal to 0. Check. Number 2, we have to integrate from minus infinity to infinity f of x dx. That's going to be integral from minus infinity to 0 dx, plus integral from 0 to 2, 1 over 8 plus 3 over 8 x dx, plus integral from 2 to infinity 0 dx. Again, we don't have to really do these integrals because they're 0 out there. So we really only have to focus on the integral in the middle. So that's going to be 1 over 8x plus 3 over 16 x squared from 0 to 2, which is going to be 2 over 8 plus 3 over 16 times 4. So this is going to be 2 over 8, which is 1 over 4, plus 3 over 4, which is 1. Check. So yes, f of x is a PDF, or can be used like a PDF. So we'll use it as a PDF. So first thing we're going to do is calculate the CDF. So first, calculate the CDF. That's what's happening here. First, calculate the CDF. Now, if x is between 0 and 2, you do the integral, you get this x over 8 plus 3x squared over 16. If you go before x equals 0, you're 0 right here. In the middle, you're that x over 8 plus 3x squared over 16. And then if you're greater than 2, you're going to be 1. So these two are always given, like the star. If you're less than 0, you're going to be 0. If you're greater than 2, you're going to be 1. So that's kind of like always going to be the first and the last value of your CDF. But the middle parts, or part in this case, you actually have to do an integral. So in this case, the integral is x over 8 plus 3x squared over 16. And just basically integrating polynomial there, and then plugging in the bounds from 0 to x. So I got my CDF. So here's the CDF on the right. What is this integral from, or basically probability that x is between 1 and 1.5? That's going to be f of 1.5 minus f of 1. So f of 1.5 is going to be 1.5 over 8 plus 3 times 1.5 squared over 16 minus 1 over 8 plus 3 over 16. And you plug and chug that out, we should get, let's see, .297, 0.297. Thank you, Caitlin. Good question. Let's see, probability x is greater than 1. Well, we said that's going to be 1 minus probability, or f of 1. That's the complement rule. Basically, the p of x greater than 1 is probability to the right of 1. So the probability to the right of 1 is 1 minus the probability to the left. So f of 1 is probability to the left of 1. So this is going to be 1 minus 1 over 8 plus 3 over 16, which is, let's see, 2, 5, 11 over 16. 11 over 16. Make sure I did that right. So 11 over 16 is 0.6875. So those are our answers. Good to go. Good to go. Again, we'll just take a second, try to soak that in, try to make sure everything makes sense. Questions? I got a question for you guys. Why haven't you smashed that like button yet? Just kidding. I'm so sorry. I can't stand it when people do that, to be honest. It's all a game. It's a game. They want to manipulate the YouTube algorithm to, promote their content because it's a game. They're chasing the YouTube algorithm. They're not chasing the goal of excellence and creating good quality videos. But I mean, I don't know. It's a double-edged sword, I guess. If you don't do it, you don't get promoted. If you do it, you get promoted. But do you really deserve it? I don't know. Maybe a computer scientist can find a better way to distribute content versus like just come up with some arbitrary algorithm that is based off these rules of likes and whatever. Anyway, apparently it works though. Now we're up to 11 likes. 12. Whoa, dang, blowing my mind. 13. That's why people do it, because it works. There you go. What the heck? What have I been doing? I'm just kidding. 15. Oh my gosh, blowing it up. Algorithm's coming for me. It's coming to get this video and snatch it away like gold from a leprechaun. I can't believe I just said that. Okay. 18. Let's see. What do you do? How do you go the other way? Like, what if we have the CDF and what if we have the CDF and we want to get the PDF? If we have the CDF, we just need to differentiate it to get the PDF because we integrated the PDF to get the CDF. Well, to go the other way, we just have to differentiate the CDF to get the PDF. It's pretty straightforward. So just like this example right here. For the uniform distribution, here's our CDF, at least where the part where we're non-zero. So then differentiating that, the place where we're non-zero for our PDF is 1 over b minus a. So these are kind of like just inverse operations. Welcome back to campus. Yes, the train in the background. Yeah, you want some merch? I'll give you some merch. Yes, I can definitely give you some merch. I'll sell you pens and calculators and yes, paper, engineering paper. Yeah, I got some merch for you. I also got avocado toast you can stuff in your face. So I'll even sell merch about avocado toast. Why not? What the heck? Definitely totally ripping off some YouTubers right now. But yeah, why not? What the heck? 23 likes. If we can get up to 45 likes, I have no idea what I'll do. I know that you guys will be blown away. I have no idea what I'll do. So stupid. This is what they do. They play some stupid mind games of like, oh yeah, I'll give you free stuff if you promote my video and like it and screw with the YouTube algorithm. Maybe I should make a channel that just screws with the YouTube algorithm. totally screws with it, just to show that it doesn't matter what your content is. You can screw with the algorithm. Okay, I'll stop talking about the stupid algorithm. Let's see, 4.2 cumulative distribution functions, percentiles. Extremely important right here. It's the percentiles. We are going to use this over and over and over and over. So, a percentile is really just a particular x value. It has probability of p to the left. So the probability to the left of the percentile is that amount. So basically like the 99th percentile, you know, that's like way over here. Let me do it in red. So somewhere over here, that'd be like the 99th percentile. So it's like 99% of the probability, or 0.9 probability, 0.99 probability is to the left. So let's think about like the median. The median is half the probability in the middle. So like half the probability to the left and half the probability to the right. So we'll call it x sub 0.5 would be the median. So, or eta of 0.5 would be the median. Half the probability is to the left and half the probability is to the right. So it's an x value. Percentiles are x values. Percentiles are x values. So it's the x value that has probability p to the left. That's what a percentile is. Probability of p to the left of that percentile, or a certain percentage of the x values or data points are to the left of that x value. So that's what a percentile is. 50th percentile, that is the median. 75th percentile, that's the third quartile. We talked about this in chapter 1 a little bit. The first quartile is the 25th percentile. Yeah, you get the idea. The median is the 50th percentile, or 0.5. So half the probabilities to the left, half the probabilities to the right. All right, example. X is the amount of product in tons sold by a manufacturer. And supposedly little f right here is a PDF. So it's a PDF. And we could go through and verify that. Then this is its corresponding CDF. So corresponding CDF. Then the probability, little p, corresponding to that percentile. So this is the corresponding percentile. Is the probability to the left, which is given by capital F. So probability to the left of eta of p is equal to p. So then just plug in eta of p to your CDF. So basically x gets replaced with eta of p, and x cubed gets replaced with eta of p cubed, right here and right here. Now that is a thing we can distribute. So we distribute it and we set it equal to p and move the p over, and we get a cubic. So this is a cubic polynomial for eta. So this is a cubic polynomial for eta of p. Let me go through those steps in a little more detail. If we have little p is equal to 3/2 times eta of p times minus eta of p cubed over 3. Then we can multiply by 2, so we get 2p equals 3 eta of p minus the 3's cancel there when I distribute, so it'd be eta of p cubed. And then we can move the 2p, let's see. Actually, we move the eta p cubed, eta of p cubed to the left. So this becomes eta of p cubed minus 3 eta of p plus 2p equals 0. And that's how they get this equation. Now that's a cubic polynomial for eta. And depending on what p-value you plug in, you can find the corresponding percentile. So if you want to find the median, you would plug in little p equals 0.5. So little p equals 0.5 would make that a 1, and then solve that cubic. That's actually this percentile, so this would be your median. The quartiles, first quartile right here, third quartile right here. If the PDF of x is symmetric, then the median is the mean, but we haven't talked about the mean, so we call it that point of symmetry. So good stuff, good stuff. A little detailed. I don't know if we'll have to do anything like that. If we do, I'll do some more examples, like more concrete examples, just to work through that. So, but yeah, we'll try to hit some more examples if I want to go over that some more in the future. That one's a little involved because it's a cubic. Now, expected values. Let's see. We may call it a day. I want to start off with expected values next time, I think. So let's call it a day. Come back with expected values on Friday. Hopefully by then your exams will be done. Somebody let me know, have you checked on the exam since last night? Like, can you see what I've written so far in that folder? I don't know if anybody's checked yet. Somebody let me know if the folder that you have that I shared with you has like an updated PDF. Like I was writing on the PDFs last night. I want to make sure. Do I have B's? Who wants to know? Why do you ask? Okay, sweet, sweet. Yeah, I don't know. Do you want to buy some honey if I do? We see red, good. Maybe I should grade in green or something. That might be a little more like, I don't know, less abrasive. We see red. Sweet. Up to 30 likes. Whoa. Yes, 5 to 10. That's right. I still have to grade 1 to 4. I'm going to go through that. I actually, sweet. I'm going to work on problems 1 through 4 today. Hopefully Dr. Ming's on my back because he's like a, what do you call that? A cattle driver. So or maybe that's a bad idea. He's cracking the whip and I'm doing the nay-nay. So he's got me going. Working on 245 as well. So I'm trying to balance out a little bit. Yeah. When are you going to promote honey? Yeah, I mean, I don't know. It's up in the air right now. Haha, see what I did there? The pollen is, okay, sorry. Yeah, I don't have bees, not right now anyway. My brother-in-law wants to get some bees. We live on like the same property, so he wants to get some bees at some point. We haven't done anything yet. We just planted a garden on Saturday. We still have some more things to plant, so but I don't have any bees right now. I'll let you know as soon as I get some bees. I can promote bees, sell it online through my merch. That sounds totally legal. Sending edible things to people. I'm glad that was the best joke you've ever heard. Tell the YouTube algorithm that was the best joke you've ever heard. Man, I missed the in-class back and forth. This has been really great today. Been missing the banter, the back and forth. I think I'm going crazy just sitting in here talking to myself, it seems like. Thanks for interacting today. It's been great. Well, I'm going to call it a day. I'll see you guys on Friday. I'll just keep working on those exams, and as soon as they're done, you'll see it in the folder. So just keep checking, and I'll let you know what your grades are. You'll see them online. So have a good have a good rest of your afternoon. I'll talk to you guys later.